EE546 Recurrent Neural Networks, and we've reached week 6. And today I'm going to be talking about CNN+RNN architectures because it makes a lot of sense to talk about them because there are a lot of very nice architectures that work with this principle and they are quite hot. I mean, they are a new topic for that matter. Okay, let's see. So far, so good as always. What we've done? Well, we've discussed what is the difference between RNN and FNN. That's how we start. And when people ask me, what is an RNN? I always tell them the same thing. Watch this first video because that's what we are, that's how we are defining it. Defining it and relative to feed-forward neural networks. Then vanilla RNN, how to train RNNs, and why it's difficult to train RNNs, which leads us to the idea of LSTM. We have studied LSTMs very well for 2 weeks. I mean, we know the formulas, we know the formulation, we know the strength of it and where does that strength come from. And the previous week, we have discussed some variations. I mean, we've done thought experiments, which were already done by many scientists in the field, and we've analyzed their designs, and we've discussed in which ways we can improve the LSTM design. Okay, actually, I haven't discussed them with you, but LSTM also very strong. It has very, it has very important weaknesses as well. Currently, LSTM and nowadays the hot topic is transformers. They are very powerful, but when something is very powerful in the literature, nobody wants to talk about their weaknesses because it doesn't, it doesn't get you published papers. However, currently, maybe in this course I'm going to talk about it, but because we are not there yet, I am a researcher in a TÜBİTAK project with Cengiz Hoca from Hacettepe University. And Cengiz Hoca was my manager in Aselsan. But he was a manager in Amazon in the United States, and he came back to the TÜBİTAK program, and he's doing his own TÜBİTAK project there. He's working on symbolic AI. Symbolic AI is like the old AI, like the Turing machine type of AI. And currently what we're working on is comparing very simple symbolic AI with respect to LSTM in very simple tasks, such as that task I've given you as an homework, which is the due date today, by the way. Understanding if the sequence is odd or even. And symbolic AI can easily solve such a problem, whereas in order to make the LSTM solve such a problem, you need to find the correct parameters, you need to train such a network. I mean, not like you guys do, you design it yourself by design, but that's not the trademark of deep learning. In deep learning, what you do is you have to give data and let it train itself. And to train such a system, that simple system, you are providing a sequence of ones, and it is trying to train itself such that it recognizes odd or even sequences, binary classification. I mean, it is so hyperparameter fragile, maybe if it's the right way to put it. So actually, LSTMs are very powerful, but there are parts of them that are very weak too. We don't discuss them here. Because that's not how you discuss them. You first learn recurrent neural networks and LSTM, and then when you're studying it, you analyze it. So maybe it is natural that the weaknesses of LSTMs are beyond the scope of this course. It may belong to a course where we discuss different types of LSTMs or different types of AI, symbolic AI with respect to this deep learning AI. So up to now, it's one of the strongest. Whatever was built, it was built on top of it. And today's hot topic, transformers, the topic of some weeks later, we are going to be comparing ourselves to LSTM. So whatever you do, you compare it to LSTM. It makes that, this makes LSTM a trademark. However, this week we are going to talk about something that LSTMs are actually known to be weak for, which is processing signals. Okay, so what I mean? Input with spatial structure. Well, spatial structure, for those who haven't heard about it, spatial structure is you have a signal-like structure in which of the data you're analyzing, the neighboring samples are correlated, like the neighboring pixels of an image, or like the neighboring samples of an audio sequence. When they are correlated, actually, it is difficult to model them with LSTMs, because LSTMs are actually designed to how can I put it? The design idea of the LSTM is to provide a type of AI which is suitable for high-level concepts. So it is like, that's why it's comparable to symbolic AI. If you provide high-level concepts to an LSTM, it works. However, if you provide the signal itself, there needs to be a mechanism before that high-level concepts that will carry the network from the signal to the high-level concept first. And actually, we know something about it. There are CNNs. That if you've taken my course in the previous semester or some of the course, that's CNN's job. CNNs can take the spatial type of spatial structured data, any type of signal, images, audio, earthquake records, accelerometer records, or I don't know, video, anything you can think of. So each sample is equally important, and they have neighboring information, spatial data. We use CNNs to get from this type of data to high-level features, such as you feed the image to a VGG or LXNet, that was the first guys. So what they provide you is high-level features. We have done this, remember. I mean, towards the last layers of the VGG or LXNet, what you had was high-level concepts like face, text, car, sky, tree, kind of. So high-level concepts, LSTMs and RNNs can process. However, signals, well, they don't. That makes at this point we can, I mean, safely think that, well, maybe CNNs or RNNs can be, their friendship can make a meaning for us. I mean, people have done it 5 years ago for us, but at this point, well, that's natural to think so. Okay, so the idea was here. The idea is about this. This lecture. The idea of this lecture is to use high-level features obtained from a CNN and feed it to an RNN. So actually, what we are going to be dealing with today is CNN plus RNN architectures. There are architectures which changes CNN in ways that they are merged with RNN models and they become somehow recurrent neural networks with some feedback structures. That's not what we are discussing today. Today we are discussing CNN plus RNN applications because they are, widely used. Okay. Actually, one of the first examples was Karpathy's and Feifei's image captioning example. In 2015, they published it in CVPR. And because they were the guys, they are kind of pioneers of this stuff. And Karpathy was mainly working on RNN these days. That's why I think he was quicker than everybody else to come up with this idea. Well, we can use the high-level features of CNNs and provide to RNNs. Because if you've checked this blog, the previous week we've talked about this blog, right? Yes, I've shown it to Ali, remember? That guy is Karpathy. And so he was quicker compared to other researchers in the field, other famous guys in the field, to apply this CNN plus RNN idea. And what he did was the first thing that you could imagine. He has used VGG with an RNN. And they've done this for image captioning. So their usage of RNN was very simple. They've used the 512 neuron RNN, simple RNN. Because I guess Karpathy in his blog also says this. Karpathy thinks that RNNs, when provided the proper inputs, these high-level type of inputs, they can do magic. And he tried this magic and yeah, he did it. So that was the idea. Here's the image, single image, not a video. They are working on single image. You feed it to VGG. The VGG will provide you some type of features, high-level features. Actually, when VGG provides you this, let me just pause this. Can I pause this? I can, I guess. Sorry. So when you feed an image to a VGG, at the last layer, to the last layers of the CNN, the encoder, you have the high-level features. Okay. But what about the fully connected layers? At the fully connected layers, since VGG is trained for classification, and since after the last fully connected layer, you have a softmax layer, actually you have something like the probability distribution. So that high-level feature here that we are going to be feeding to the RNN is a type of probability distribution. And these guys did something, strange. They have fed this like a hidden state. And they've started with some inputs and they've got some outputs. And it was their architecture. So, and the hidden state changed. And the system provided an output of a series of words, which will in the end will look like a caption for that image. So what kind of captions? For example, what kinds of captions will depend on what kind of a training set they used. And the training set was like this. There are many different image captioning training sets. Most of them are trained with the famous Mechanical Turk. Mechanical Turk is a website where researchers or some companies collect labeled data. There are different types of experiments. You can design your experiment. And for a long time, starting with 2005, this ImageNet challenge started collecting these kind of image captions for different types of images. So for example, for this image, the consensus label caption was a tabby cat is leaning on a wooden table with one paw on a laser mouse and the other one black laptop. Quite a strange sentence. I think it's from the paper, and that they've deliberately chosen such a thing because you've got very, very strange images and sentences and captions as well. So that's how you train the system. So the image going to CNN and this captions being fed to the recurrent neural network. So nice. How do you train a recurrent neural network with captions? That's a detail that I'm not going to be talking about in today, but there are different cost functions for that. I strongly recommend you you analyze them if you are going to be working on image captioning, whatever. So this was the structure. And they had many nice results. For example, these are some examples, and this is Karpathy. I just wanted to put this because the famous guys I put on this corner remember this Karpathy. Well, in general, the network created very accurate results, and it was a very, very, for that time, it was a very nice leap for image captioning. And for example, man in black shirt is playing guitar. Construction worker in orange safety vest is working on a road. Two young girls are playing with Lego toy, although this lady is not, young compared to this lady. A proper captioning would be a baby and her mother is playing Lego. A boy is doing a backflip on a wakeboard. Very good. So some example sentence, and when you analyze the sentences, there are mistakes. For example, this is not a wakeboard, and two young girls is not a proper way of, they are not old, of course, but it's not a proper way of captioning it. A human caption wouldn't look like that, at least. So, but if, after analysis, the network was quite successful in many senses. For example, in the network, a man in black shirt is playing guitar caption does not exist. So the network has the capability to collect objects and create the necessary grammar for a sentence that looks like a real sentence, right? Many lectures, the playing card is a test case, and you don't have a similar, you have this sentence in the training set, which is fantastic. I mean, it is like the guy can talk. You just show the images and it can talk. Actually, it's trying to imitate that behavior. So there are two things that this network learned. I mean, it learned the relation between the objects and, I mean, the objects being provided as high-level features through the VGG's final connected layer already provided. So the relation between the objects, which word corresponds to which high-level feature in VGG's output, plus the English grammar. So it could learn two things at the same time so that it could produce very nice sentences. Therefore, the network really learns how to combine these in a general and meaningful result. That's the idea. And although these results look very impressive, there are some limitations of the network. For example, the model can only handle one specific array of pixels with fixed resolution because of the VGG. And actually, that's not the only weak spot. Actually, there are demos that you can test this system, and if you provide different types of images, I mean different than the ones that were provided in the training during the training session, you get funny results. I'm going to do it, by the way. Okay, this is the next one. Oh no, this is the paper, I'm sorry. So this is one of the pioneering studies, Karpati and Fefeli. Actually, after this study, the field of image captioning was flooded by various CNNRNN architectures because we had different types of CNNs, and the RNNs and LSTMs were, I mean, the importance of LSTM was just being understood by those days, and the area was flooded. Then the area is now even flooded by CNN+RNN studies. Actually, I'm going to show you a study to the end, towards the end of the lecture, a study of this year, 2021, which is a CNNRNN network for earthquakes, which we are trying to do for some time with Salih Hocam and one of our master students, who is not here at the moment, I guess. Yes, who's not here right now. So, okay. Okay, I cannot see my mouse. Okay, so another one, which was an improved version, was show and tell. But before I pass to that one, I'd like to show you some results, which is fun. Let me show you some results. So this is one. So for example, this website that provides you with, you can upload photos and it creates network. So you just provide this photo and you generate caption it. It generates some captions, some results, number of results. So it is a very nice result. I mean, if you just look at it, let me try to make it larger for you if I can. Zoom this here. So this is a double-decker bus driving down a street. Not bad. It doesn't look like a double-decker bus, but it's okay. A bus driving down a street next to a building. Not bad. Very good. But I'm going to be trying a new one. Let's do it. Generate caption. This one is a bit different than the ones, I mean, the aspect ratio is quite different than the ones that has been used in training of the VGG, for starters. A woman holding a Nintendo Wii game controller. I guess because my hands are on her head, that's why. Little girl, very good, holding a Nintendo Wii game controller, obsessed with Nintendo. Little girl that is holding a toothbrush. Not bad, again. The best one is little girl holding her teeth in the bathroom, brushing her teeth in the bathroom. So for some reason, because of the teeth maybe, because of this smile, obsessed with toothbrushes or Nintendo, I don't know. So the results are not always good, but still, it looks like real AI. I mean, if there was a robot, and when I showed the AI some pictures, the robot, or the robot looking at, I mean, the surrounding and building up sentences like this, I would think that is kind of a C-3PO. I mean, at least. So it was a leap in that sense. Okay, okay, you could try this. It's a very fun website. I played with it so much. So funny. Please do it. Okay, so I get back to my slides. Guys, after Karpathy and Fefeli, which was, in my opinion, a primitive approach because they didn't properly use the best RNN, which is an LSTM for that, for those days, or they didn't use the best CNN, or I don't think that they've used the best way to use the CNN. They could, I mean, for example, provide features from multiple levels, from the fully connected layer and the convolution layers. They could have tried anything. They just tried the first thing they could, and they did get good results. The second one is called Chauvin, and it's very famous, guys. Nowadays, if you do image captioning, you have to benchmark your results with Chauvin. Chauvin is one of the best, and it's from Google. And since it's from Google, they've used their own kind of CNNs, which is the exception network, as you remember from the previous year semester's course. And the architecture was, the idea was the same. This time it was a deep CNN with an LSTM. Okay. So again, you just get a deep CNN plus the RNN, and the RNN creating inputs for you. So until the RNN decides that the output is a dot, it will create a sentence. That's why we always said we use LSTMs for varying length input, remember? But it is a special case. The input is not varying length. However, the output is varying length. That's why we choose to use LSTMs. So maybe we should have said in the previous weeks, RNNs are for both varying length inputs and varying length outputs, we should have said, truly. Okay, so a nice example. So yes, a group of people shopping at an outdoor market. They always show the best results on their papers. We also do, so I don't blame them. This is one of the good results. Or there are many vegetables at the fruit stand. And as far as I remember, this guy could create more than one sentence. Yes, it generates complete sentences in natural language. And this is the idea. Do you remember this? Do you remember this shape? Well, it is the exception nets. Also called the Google nets, because these guys are from Google. Of course, they are going to use their own net. And this is LSTM unrolled in time, so there's a single LSTM. So LSTM combined model with CNN embedder. Very good. I mean, it was published in 2015 or 2016. I don't remember, but 2015 and 16. So still one of the best, one of the first results, but still even today is one of the best results. So this architecture is appropriate for problems like you have a spatial structure in their input, such as 2D structure of pixels or pixels, I don't know, 1D sound. Or the 1D structure of words, I mean, at the output. So having a temporal structure in their outputs is the order of images in a video or words or in a text or required generation. Oh, yes, you could just generalize this idea to videos and longer text in which you come to an end, not with a dot, but with a paragraph end, for example. This is what this guy does, so that you could create multiple sentences. You can just generalize this problem to different examples. I mean, for example, this is a very nice project title. I mean, you could, as you've seen, the networks trained so far are trained in ImageNet or CocoNet. Coco, one of the important data sets, image captioning data sets. And so they are good at captioning images which are similar to their training set. You want to caption different types of images. I don't know, artistic images or sports images, for example. Maybe you could transfer these networks to them and study within a small network in which you have labeled it yourself for that specific problem. I mean, you could label some number of images for this project and work on some transfer learning examples. That would have been a nice study project, even thesis. Okay. So after this, I mean, the studies on different types of LSTM or LSTM on different types of spatial signals or inputs exploded. One of the nice examples is these French guys. They've used the CNN LSTM architecture for speech image recognition. So speech emotion recognition, I'm sorry. What they did was they provided the speech sound signal. They've calculated the spectrogram, log spectrogram. Spectrogram is for small periods of time, you just cut the time signal sound. For those small time pieces, you calculate the Fourier transform. So you have a Fourier transform image for that part of the sound. So when you do this for all sound pieces, you have a time versus frequency map, which is the spectrogram. And then you take the log of it because the energy of the, the energy, the square, the magnitude of the frequency domain can grow very fast. So when you take the log of that frequency energy of that band, it is log spectrogram. So you get log spectrogram, which is a sequence. Pieces you are feeding. You feed them to a CNN. So you get some pieces of sound in a high level. So those sounds, those things, those frequencies in sound, maybe when you're crying, you're creating different frequency sounds. When you're laughing, you're creating different frequency sounds. So you have these, and you feed them to a BLSTM. And with a softmax layer, they do classification. And they do BLSTM, which makes us think that since we know what a BLSTM is from the previous week, not the previous week, they thought that, maybe they experimented that, I don't remember the paper, BLSTM was a proper choice for speech emotion recognition. Because for a sentence to be called a funny sentence or a sad sentence, maybe you should just check the sentence from the start to end, from end to start, maybe. I don't know, I cannot speculate now for that. I'm very tired in a Friday evening, but apparently they've used a BLSTM, and in their paper, if they have advocated enough, there could be a reason for this. And I don't know if, I don't remember, and I don't know if they did, but if they did such a study, that would make us think that, wow, emotion of a speaker in a sound signal have a relation within that sound, which is an two-way relation from start to end and from end to start. That's important. That's an important invention for that. For that problem, in my opinion. Okay. Okay. Another one. Well, we said you could apply it to sound. You could apply it to videos. Action cognition. So what these guys did was they applied it to video signals. These are applications, guys. And as you can see, the quality of the papers, and these are nice papers, but where they are published, when I just looked for them, became, IEEE Access is a very important journal, but not as striking as CVPR, as Karpathy's study, although these ones are technically more sophisticated, because when that idea exploded, everybody started trying them. And in 2007, these guys tried the CNN plus LSTM for action cognition. So you had actions, sequence of frames being fed to a CNN. From the full connected layers, we have some types of layers. They used MLSTMs. Well, that's a multiplicative LSTMs. I don't know. They have their reasons, I guess. Then they have two-layer LSTM, I guess. Forward layer. So is a B LSTM or B multiplicative LSTM? I don't know. Let's check. You check the paper. And at the output, they did a softmax to classify. I mean, it makes sense. I mean, you can apply it to anything. Another one. An LSTM, it's 2019. LSTM and CNN-based assembly network framework for arrhythmia classification. Exactly. What these guys did was they worked on ECG signals, EKG in Turkish, that the rate of your heart being monitored by a sensor. And in your sensor, I mean, we sometimes experience arrhythmias, and it's difficult to get them. And what they have studied this problem with an LSTM only like 2 years ago. And what I believe is, guys, there are very cheap bands. I have one of the bands which you can buy for $20, $25. And in those bands, they have heart rate sensors. Soon, those sensors will provide arrhythmia classification. They cannot right now because these medical stuff has many complications, and they just do not want to do it, because when you say such a thing, it becomes a legal issue and they don't want to do it. But soon it's going to be part of the bands. And those bands are going to be a part of your insurance company. So that if you wear that band, you most probably have an early warning for an arrhythmia or heart attack by detecting an arrhythmia like this. And they had this. What they did was they have taken the ECG segments, some processing. What was the SDL? What was the SDL? What was the SDL? I remember reading this paper. I don't remember the SDL. So it's like a pre-processing, guys. Then fed it to the CNN layer and the LSTM layer, being fused a different approach, and they classified this is normal heart rate, or this is a arrhythmical heart rate, etc. You could just use the regular CNN plus LSTM example as well. I think MATLAB has one of these in its sample networks. When you're trying to learn their toolboxes, they provide networks. And MATLAB has an example for it, as far as I remember. Okay, another one. CNN and LSTM based approach to classifying transient radio frequency interface. Radio frequency, these guys listen to radios, I mean, things that come from the outer space in different bands, and there are very, I mean, interference with, I mean, every different devices on the Earth. So non-radio waves that are created by radio stations or other stuff. So what they're trying to do is they're trying to classify these transient radio frequency interferences so that they know what is really coming from outside and what is actually noise coming from inside. And it's a very nice study. So it's one of the cases that you can apply. So the RF signal being fed to the 1D CNN, because RF signal is 1D. Then LSTM, which is a BLSTM, because you both feed it backwards and forwards. And with the you have a fully connected layer for decision and a softmax for classification. Well, this should sound very, I mean, I don't know, natural to you. You should feel like, well, that's the obvious way of doing things. You should be thinking. And what they did was that these were the classes at the softmax there. These were the classes: fluorescent lamps, power tools, AC motors, things, these transient radio frequency interferences. So when they had one, they could classify it and maybe work on it, just retrieve the signal. Okay. Nice. Which is applied to, this is another one. They have used CNN plus LSTM models for time series. Time series is any type of data that is a function of time. And actually these stock market prices or other things these are very chaotic series. And it's very difficult to model them. People, before the ages of deep learning and LSTM, people have been working on these with statistical models and so much, and they couldn't get any results. I mean, however, with LSTMs, there is some hope. I mean, I haven't heard of some architecture which works very nice for all time series and stock markets. But I know that many e-finance algorithms use these LSTMs so that they do these stock operations automatically, and these buy and sell stuff, and they just create some bots to do these jobs, and they use AI mechanisms like LSTMs, and this is an example. So this model is a forecast for stock prices. So it is just trying to guess what the next value of that stock would be. It's very nice. RE idea, 2020, by the way, guys. So it's the input layer. You're providing time series data, you have convolutional layers, you have pooling layers, and it's a multi-scale architecture. With different pooling layers, you are getting different scales of the data in time. In time, scale means different dependencies. So maybe this pooling layer summarizes the last 20 minutes. This pooling layer summarizes the last hours. This one last days and last weeks, kind of, so that you model that behavior in different levels. And you feed it to the LSTMs, and you at the output layer, you just read what you have and you classify. And they try to guess the stock prices. And the one that I mentioned, a 2021 paper, guys, because this is what we've been working on. Because when I was preparing for the slides, I just wanted to check, because we are working on this with Salih Hoca and we are preparing a project proposal. And we just saw this, we were very unhappy. But that's the nature of it. I mean, academia, there's always this, you try to publish something and people publish it. However, that's not the right way to do it. Should we tell it? Because we put it on YouTube. Anyways, what this guy did was, this is an accelerometer data. This is an earthquake. So at a station, in one of the sensors that was placed in one of the directions. In some directions, they've placed it, thanks to Salih Hoca, I've learned all of these in the last year. In a station, they place these sensors in 3 orthogonal directions. The Earth directions, actually, from north to south, from east to west, and from up to down in the gravity direction. So this is one of them. Let's say it's the gravity direction. This is most probably not the gravity direction, but I don't know. Let's say this. So
it's the vertical.
Thank you, vertical. Attım tuttu yani. It's the vertical. Thank you, Salih Hocam. So since earthquake engineers, they understand from the shape of it, which makes us think that if earthquake engineers can see it and get an idea about it, maybe our AI systems can get an idea about it, we think. And there are stages of, let me say, phases of an earthquake signal coming in, which are called the S and P waves. The earthquake hits and it travels along the way. And during its travel, some of the waves travel fast and some of the waves travel slower. So you feel the earthquake. I mean, the earthquake is felt by the sensors and people with respect to these phases. And actually, the phases can be seen at the very start of the earthquake. The first P phase and then the S phase hit. And you have the signal. So what can you do? There are many things you can think of. And this paper is trying to do an early warning system. For example, for the last 3 days, you have been gathering some weak vibrations. However, those vibrations, when maybe studied in an AI system, which can use the advantage of using many different records that was previously recorded on that station, you could just make a guess. For example, you can say that, well, such a behavior previously created a 6.5 earthquake in 5 hours, say. So that's an early warning system. So that's a type of regression problem if you're trying to make a time estimation. But if you're trying to make a flag rise and fall, like in 24 hours, there's a danger of a strong earthquake. That's a classification problem, and even binary classification problem. So you can design anything, or it's not the only early warning system. You can, using the earthquake signals, you can try to estimate different parameters as well. So these are very hot topics. I mean, implementing these CNN+RNN techniques to different types of problems is one of the hottest current topics. So it is becoming an engineering problem even. However, I mean, there are not enough machine learning engineers to deal with this stuff. So you guys are the engineers or the researchers of this stuff. Okay, I think we have the idea. So that was their idea, right? Earthquake accelerogram records. So what they did was they had the input signal features, some convolutional layers, some fully connected layers, also called the dense layers, and class probabilities. This is the CNN. and they have fed it to the LSTM. And actually, no, actually they've used the LSTM and CNN separately, so that was not a proper way of using it. That's why I said. And they tried to make some guesses. So I'm not going to go into their idea, but that's one of the things that you can work on. Okay, so there are some links here. Guys, I was planning to do live code on CNNRNN architecture this week, and I tried to. And it is when I try to make a live code for you, what I do is I check the internet, GitHub mainly, and try to find the best code, because not all GitHub implementations are great. And I found the one. It is this Muggins. It is this Muggins. I'm going to show you. Where is Muggins? Where are you, Muggins? It is this. Yes, it is here. It is Chauvin, which you can try and change. However, in order to be able to train it, it is based on Coco image set. And actually, there is a Python library for Coco image sets and its usable functions, for example. It's called PyCoco tools, as far as I remember. I was trying to download it and I couldn't have the find the time, because I'm crazy busy these days trying to just catch up with both sides, you know. So guys, I couldn't finish it. I was planning to, but if you're planning on image captioning, this is a very nice code. It's a very structured code, which you can train, retrain. It has very nice explanations and comments. This is the best one I found. Study this. And just like I said, for example, trying to do a transfer learning problem for image captioning to a limited data set where you have your even, not even, your weird labels and captionings, so that you could just imitate that weird behavior. So your system would really like sound like C3PO. Okay, since we don't have the live code, that's all on my side, guys. And before I finish, I'm going to get your questions, don't worry. We have the midterm next week. The midterm will be an hourly take-home exam, hourly. So I'm going to give you so you'll have the access to it like 6 p.m. next week today, and you'll be uploading it midnight, kind of. So, and the other week we have the holiday. And so we have the next lecture in 3 weeks then. So, okay. So this became a lie. Okay, that's it on my side. Any questions about CNN and RNN architectures? Then any questions about the course?